Hi everybody, welcome back. Today we're going to cover 8.2. Very sadly, this is the last new topic required by the AP, so it's the last new topic and last video that we'll have until after the exam in May. Hold on a second. Makes me pretty sad. Pause the video here if you need to go get yourself a Kleenex, because I know you're pretty upset about not getting to watch any more videos for a few months. Today we're going to compare rates of growth of two different functions, and we're going to use limits in order to do that. And we're just really going to talk through a series of examples that are right inside of your textbook. First, our definition, how we're going to do this, is we're always going to be using a limit as x approaches infinity, and to compare our two functions, whatever they are, we're going to do a limit as x goes to infinity, and we're going to make a fraction out of it. And all that's going to happen is if we ever get an answer of infinity when we do that limit problem, we'll be able to conclude that the top function was the faster function. So if we do this limit problem and get an answer of infinity, we'll say f of x grows faster. And the reverse of that is true, so when we do the limit problem as x goes to infinity, if we ever get 0 for our answer, then we'll conclude that whatever function we put in the denominator is what is growing faster. And then the only other possibility besides infinity or 0 is there might be some times when we do the limit as x approaches infinity where we get some sort of constant non-zero answer. And in that case, what we'll conclude is that both functions grow at exactly the same rate. So for all of our problems, when we're asked to compare their growth rates, we're either going to say that we're either going to name which function is faster, or some problems might ask us to find the slower one, or we might say that they grow at the same rate. Okay, let's just talk through three different examples. Here's a problem straight out of the book where we're asked to compare the function e to the x and x squared. It doesn't matter which function we place on top. It'll work itself out. In this case, the authors of the book chose to put the e to the x on top. So they set up exactly what we just talked about. They do a limit as x approaches infinity of e to the x over x squared. We should use whatever methods we learned either in Chapter 2. Sometimes we might use the new method, L'Hopital's rule, which we do here. Remember, try substituting first. E to the infinity is infinity. Infinity squared does approach infinity also, so there's that indeterminate form. So what you see them do here is they keep the same limit, but do the derivative. Derivative of e to the x is e to the x. Derivative of x squared is 2x. Try it again. E to the infinity is still infinity. 2 times infinity, still approaching infinity. Use L'Hopital's rule again. Derivatives. This time we get infinity over 2, and so if your numerator is approaching infinity, overall your whole thing is approaching infinity. And from what we just talked about on the last slide, that means that the upper function is what is faster here. So we could say it is faster. And they had already concluded that up above. So that's how they decided that e to the x grows faster. Okay, pause and look through that a little further if you need to. Write some questions down if you have them, and I'm happy to answer them in class. Example 2 from the book. They tell us to compare natural log of x, and I think I'm just going to talk about the one where we compare natural log of x to x. Once again, to do this analytically, which is what I'm going to want you to do, we'll do a limit as x approaches infinity. Even if you run into any problems, even if you are 100% sure without doing any work that one is faster than another, I still want you to go through the process. This is how we'll definitively prove it. They put natural log of x on top and an x on the bottom. They didn't show it this time, but if you do natural log of infinity, that approaches infinity. Infinity approaches infinity. So another case where L'Hopital's rule applies. Derivative of natural log is 1 over x, derivative of x is 1. Here's a case where we don't just want to necessarily sub into it, but simplify this expression, and 1 over x divided by 1 does simplify to 1 over x. Then attempt to sub in again, you get 1 over infinity, and sure enough, if your denominator is approaching infinity, your overall answer is 0. And we said if our answer to this limit problem ends up being 0, we know that the faster function is the bottom, and this question asked us to prove that natural log of x was slower. So if x is faster, then natural log of x must be slower. Okay, so there's example 2. And then just one last one. What I really like about this problem is there's a trap waiting for us here. This one tells us to compare two different logs. So log base a of x and log base b of x. And they've given away the answer that it grows at the same rate, but let's assume that we are asked to find which one is faster here. Do a limit as x approaches infinity. Just pick one of them to be the top one to be the bottom one. It looks like it's a case, if we just kind of blindly start subbing in, we'd get log of infinity and another log of infinity, which both of those would approach infinity. We might head down the wrong route. It's a bit complicated to find derivatives of this, so there's a little bit of an easier way. There's that change of base formula that they use here, so they're not using the L'Hopital's. They just use that change of base that says you can take natural log of x over the natural log of this a part here. So that's what they've done. They also just use the algebra rule of change of base, so you can do natural log of x over natural log of b. That's what they place here. And I'm going to write this out a little bit differently. They have natural log of x over natural log of a, and if you're dividing by this other fraction, that's the same as multiplying by the reciprocal. So it looks like this. And then you can see that the natural logs cancel out. That's where the natural log of b over natural log of a comes from. And we do need to keep in mind they told us up above that a and b are constant numbers. So if you take a natural log of a constant, you do get a constant answer. Same on the bottom. If you have a constant divided by a constant, it's still a constant, which is non-zero. And that goes back to our very first slide. We said if we get a constant answer that's not 0, we would say that the original two functions grow at the same rate. So that's how we would decide in this one, that they grow at the same rate. So when you do the homework, be on the lookout for this type of problem. If possible, avoid using other complicated methods. You can just use some algebra sometimes to make things look nicer, which makes our whole problem a whole lot easier. Alright, sadly I think that's it. Again, come in with any questions. We'll practice this in class a little bit. I'll see you guys in class. Bye-bye.